Okay, it's 3:05, so let's get started. Two announcements: quiz 8's out, due Saturday as usual, and homework 4 is out. You have an extra week to do part 1, so that's good. Any questions before we start? Or rather, your questions are much more important than this, so this is really where it starts. So are there any questions about any of the material at all? Going once, going twice. No, you can ask at any point. But. Okay, so what was the main thing we talked about last week?
PDA to CFG?
Yeah, so converting a PDA to a CFG. And in recitations and in lectures before that, we actually showed the other way about how to convert an arbitrary CFG to a PDA. So if I can show this direction, what can I immediately claim? Yeah, they're equivalent. Yeah, I can convert back and forth as necessary, just like with NFAs and DFAs. So, how am I going to work with an arbitrary PDA to convert it to a CFG? Doesn't seem really clear as to how to do that. So let's say that we're looking at an arbitrary PDA. Say that one. It's not a box, obviously, but let's say that it has 2 accept states. It may have more, it may have fewer, but let's just say it has 2. Actually, a nice exercise is that for any fixed integer, you can convert any PDA to another one that has exactly that number of final states. I'll leave that as an exercise. But suppose I have a PDA that looks like this, and now what was the thing that we had to do to the PDA to make it easier to work with in a sense? What was the first thing that we did?
Add a symbol. No. Is the dollar sign?
Not necessarily as the bottom of stack marker, because this is an arbitrary PDA. I don't know what it does. Well, let's see. What does the stack start out as? Empty. What does it end as? Does it have to be empty? No. Well, maybe if we could enforce it to be, or at least have a way for it to be empty when it accepts, that might be a good idea. So how did we do that? Well, like we did with the GNFA method, we made a new start state, but I don't need to make one here. But what did we do about the final states? Yeah, we made a new one, a single final state. So that must mean I make all the old final states now not final. And then how do I hook up this machine to this new state? Yeah, triple epsilon transition. Yep. And what is the reason? Yeah, so obviously I better not read, in which case I would change the language. I better not pop because the stack might be empty here. I don't know. It could be empty. So I don't want the possibility of popping something prematurely. Well, I could push something on, but there's no reason to do so. But I want the stack to be empty, and I just deferred the problem over to here. The stack could still not be empty. So how can I make it become empty? Once I get to that final state.
Pop any arbitrary value off.
Right, just pop everything off. Right. So, again, I better not read on these transitions, so I'm not going to read on them. I'm going to pop each of the characters in the stack complement and not push anything. So for every single stack character, I'm going to have a self loop at the end that just pops it off. And then you say, well, what if the stack was empty when we started, when we were in the original final state, then we came over, then I can't do anything. The stack's empty. so I won't accept, right?
You're already in the final state.
I'm already in the final state, and I assume I've read all the input. So, do I have to take these transitions? No. So what this guarantees to us is, it doesn't force us to end with an empty stack, but it gives us a way to do so. And that's all we really need. So maybe let's look at what happens. So let's say we're looking at time versus the stack height on whatever string. I'm not necessarily concerned. But we just said that all PDAs start empty. We don't have to end empty, but we have a way to do so. So let's say we end empty. And then let's see what happens. Maybe what happens is that it is flat for a while, then it comes up, flat for a while, up, then maybe flat for one transition down, then does crazy things, and then eventually comes down to zero. That could happen, right? Because we have transitions that do nothing to the stack height. For this push right here, and this pop right here, they end up at the same stack height, or they start out at the same stack height as when they end. But do I guarantee anything about what happened on those two transitions? I claim you can't. And why is that? Let's say that this push pushed an A onto the stack. So that A is on top of the stack now. And let's suppose the one transition that makes the stack height the same, let's say it pops and pushes on the same transition. Let's say it pops an A and pushes a B. Well, once I do that transition, what's on the stack? A B. Then I do a pop of B. So this push and this pop have nothing to do with each other. That's not really helpful, right? But could I make it so that it is helpful? Maybe what I can do is, I don't want these stack heights to ever be flat when I do a transition. I want them to either go up by one or down by one. Could I guarantee that? Yeah, well, the transitions that do exactly one of the two operations, they're definitely going to do that. There's no problem there. It's just the ones that neither push or pop, and the ones that do both push and pop, those are the ones that are causing us trouble. So let's look at both of those cases. So the first one is I do neither operation, and the second one is I do both operations. When I'm looking at the push and pop transitions here, am I concerned in this diagram of what I read on those transitions? No, I'm only concerned about the stack height. So I may or may not read something on here, it doesn't matter. So let's say I read an A in both cases, it could be empty. Well, is there a way that I could simulate this do nothing transition with ones that actually do something? Is there a way to do that? Yeah, how would I do it? Yeah, so push whatever symbol I want, then I pop what? The same symbol. Because I want to end up with the same stack I started with. So I'm going to transform this into two transitions, where the first one pushes some arbitrary symbol. Why can it be arbitrary? Because I'm just going to pop it off in the next guy anyway. So I'm just going to push an arbitrary symbol on. I'm going to call it X, let's say. Then obviously, in the next transition, I better pop the X and push nothing. Okay? Well, in terms of reading, let's say I read an A. Does it matter which of these two transitions read? No, I claim not, because if both of them read actually, then I will change the language, because this transition only read one character, but if I read on both of these, it would read two. So I gotta choose which one reads, but it actually doesn't matter which. So let's just say I do it on the first one, but it doesn't matter which one. Okay. All right. Well, how am I going to do the one where I do both push and pop? Yeah, so which of the two operations am I doing first, the push or the pop?
Pop.
The pop, right? Because if I did push first, then if I push first, the thing I wanted to pop is not on the top of the stack anymore. So I better pop first. Well, what thing am I popping? I'm popping a B. So I better pop a B and then push nothing. And for the same reason, I should read, let's just say I read on the first transition, then obviously the second transition is not going to pop, but it's going to push a C, and it's not going to read in this case. Okay? Any questions on how we were able to do that? All I'm doing is simulation of the original transition. Okay, so now we're getting somewhere. We're getting to a point where we don't have a diagram like this anymore. We have something that we can actually say something about. So what do I know the first transition does? It must push. Because it can't pop, and it can't stay at the same height. So we know that. And for the same reason, we know the last one pops, because there's no way I can push to get to 0 stack height. Okay, so that's good. So, and in between, it may do whatever. It may come all the way back down to 0, but it's never flat anywhere. Okay, so that's good. So now I think we can make the CFG. So now we got to think about what are the variables, terminals, start variable, and the rules. So what are the variables going to be? Well, it doesn't seem immediately clear. So I'm going to give you some intuition. For the PDA, what states can help me figure out what the language of the PDA is? From where to where? From the start state to the single final state. I don't have multiple final states, I have a single final state. So I can think of this language of this PDA as anything that takes me from this start state to the final state. Okay, so that's helpful. But what do I know about the stack in both cases?
It's empty.
It's empty. And it starts empty. So you can think of this as starting at some whatever stack height or stack contents, ending at the same stack contents. In both of these cases it's empty, but for any arbitrary transition or any pair of states, this represents all the strings you can get from one state to any other state with the same stack height, without changing the stack height at all. From empty stack to empty stack. Okay, so that's helpful. So now we gotta think of how to represent all pairs of states. Well, think about it. May I possibly need this transition to figure out the language of the PDA? May I need it? Yeah, I might need it in general. Like, for example, if we had a transition system like this, then I definitely need it. So, in general, I can't bar any pairs of states. I gotta look at every single pair. Okay, so the way we did that was we represented them as variables with A and 2 subscripts, P and Q, where P and Q are states. Okay. So all this means is that this variable right here will generate all strings that take me from state P to state Q with the same stack height. So for that reason, what is the start variable? From P to Q. Well, it's definitely going to be of the form A sub something. Right. One start state to the final state. So the language of the PDA is from the start state to the final state. Well, that's just Q0, QF, where QF is the single final state. It's pretty neat how all this is set up. By having a single final state, I can guarantee what the start variable is. Okay, let's start thinking about this. I want to know eventually how to get from the start state to the final state. That's my goal. But let's suppose that I know how to get from this start state to this intermediary state. Let's suppose I know how to do that with the same stack height. And I know how to get from that intermediary state to the final state with the same stack height. Do I know how to get from the start to the final state with the same stack height? Yeah, it's just any string that takes me from the start state to there concatenated with any string that takes me from here to the state that I want to get to. Okay? So you can think of this as, if I can solve both subproblems, then I know the general solution. So all of this really is just a bunch of subproblems, and then you combine them all together. Okay. So now we're now ready to make the rules. So let's make the rules. Oh, and one thing. It's nice that we can get the terminals of the grammar for free, because those are just the input characters here, because it's the same language. So now let's do the rules. What is a really easy set of rules that I can make?
Normal form rules?
What's that?
Rules in the form of constant normal form?
We'll get to those. But let's consider that I'm in some state P, and I gotta figure out how to get to myself with the same stack height. There may be many ways to do that, but what's one way to do it? Could I not apply a transition? If I don't apply a transition, will I change the stack height or change state? No, I won't, because I didn't apply a transition. So what string did I just generate in the process? Empty string. So this definitely can generate the empty string. It may generate other things, but it generates that for sure. And here's some other intuition as to why that's correct. It's correct for that reason, but here's another reason. Suppose you're looking at a peak here, where the stack comes up and then reaches a point and then comes back down. Well, let's see. If you look at the very peak, I'm going to be generating variables as I'm going up. Then I'm going to have a variable sitting once I get to the top. Once I'm at the top, that variable has to disappear. And how do I make a variable disappear without adding anything to the string generated? Generate an empty string. Because once I'm up there, the state, if you look at where it comes from both sides, it goes to the same state. So I start and end in the same state. So the variable has to disappear, and epsilon is one way to do it. Okay? Okay, so now let's think about this scenario where I know how to do two subproblems, and then I combine them together. Could the stack come back down to 0 as I did here? Yeah, I assume that the stack won't be popped when it's empty, but it could come back down to empty and then be then pushed on something else. So let's consider that scenario. Let's say in general I'm at state P, then at state Q it comes back down to 0, or wherever P started at, and state R is the state that I want to get to. So my goal is to get from P to R. That's my goal. So I want to know how to get from P to R. Could I use Q to help me? Yeah, how would I do it? Right, yeah. So if I know how to get from P to Q, same stack height, and I know how to get from Q to R, same stack height. Do I know how to get from P to R, same stack height? I better know. So if I know how to get from P to Q, and I concatenate anything that takes me from Q to R, same stack height, then I know how to get the theta. Okay? For these two rules, other than looking at the states, did I look at the PDA at all? At the transitions of the PDA? No, I didn't look at any transition here. So these two sets of rules are blindly made by just looking at the set of states. So for that reason, this definitely doesn't work if I just left it at that, because I didn't look at the transitions at all. So now we gotta look at the transitions. So let's see. Let's say that this pop right here is the first time it comes back down to 0. Let's just say. What do I know about this first push and that pop? Well, they end up at the same stack height, so that must mean the push, whatever I pushed, is the same thing as the thing I popped. Because I don't have that flat situation we had earlier. So let's look at that a little bit more magnified. So I have this push right here, it does some stuff in the middle, and then it comes back down to Earth. Okay, well, did this first transition, did it pop anything? No, because it can only do one of them, operations. Let's say that it pops nothing and pushes some character X, or whatever that symbol is. What do I know about that last transition? It pops an X, and it doesn't push anything either. So we can infer a lot. Well, could these two transitions read? Or not read? They could read, they might not read. So in general, they may or may not read. So let's just say that they do read. But I could substitute epsilon for both of those or one of them, if the case may be. Well, these 4 points are states of the PDA. So let's just give them names. So let's say that that guy's P, that guy's Q, and then the two intermediary ones are R and S. Okay. Well, I want to know how to get from P to Q. That's my goal. So I want to know how to get from P to Q. What is something that I know how to do via here? That's a subproblem. Or I'm assuming I know how to do it.
Now to get to Q to R? I mean, P to R?
From which one?
P to R?
As a subproblem, though. I think it's from R to S, right? It's like an inductive definition. I know how to do most of the work right here. There's just a little extra work to do. So I'm assuming I know how to do ARS. I'm assuming I know how to do that. Well, using ARS, could I get something for APQ? Well, did I read anything on the push transition? Yeah, I read an A. Yeah, I read an A. So I read an A, concatenated with anything that ARS could make, concatenated with what? The character I read on the pop transition, which is a B. So that is the rule that I make. Okay? So all I'm really looking for here is, for some transition that pushes something, I gotta find some other transition that pops the exact same thing. Did I assume anything about what these 4 states were? Did I assume anything? Other than the fact that they're states? No, they could all be different states, they could all be the same state. Okay? Cool, so I think we're ready. Any questions about this? So all it is subproblems. Oh, that should make sense. This should be fine. So here's the PDA, 3 states, nice and good. So I want to convert it to a CFG. So do we have, well, we got to do our checks, remember. Do we have a single final state? Yep, we have a single final state. Let's see. I could add transitions that pop, but is this PDA, oh, first off, does every transition do exactly one of push or pop? Well, this one does a push, this one does only pop, does only push, does only pop, does only pop. So the transitions look good, right? Or is there something up with the transitions? I'll give you a hint. It has something to do with the self loop on Q2. For these three transitions, do they read? No, none of them read, because when I was in the original file state, I assume I've read all the input. What does that transition do on Q2? It reads. So I can't do it. I can't just blindly just start making rules. I gotta convert it to the right form. So I better make this not final. And then what do I do instead? Don't all answer at once. Yeah, triple epsilon to what? I do minus state. Good. So triple epsilon over here. And then remember, we gotta add these popping off all the rest of the stack transitions over here. So I gotta add those guys on. So epsilon A to epsilon, epsilon B to epsilon. But the stack alphabet may have more than just A or B, but I'm just gonna assume that it's A and B here. Just for simplicity. Okay. Is the PDA now ready? Or is there something we need to fix? Does my tone help? What needs to be fixed about this PDA? Pointing to it. Yeah, I have this transition that does neither operation. So how do we fix a transition? I guess now I erased it. How do I fix a transition that does neither push nor pop? Yeah, exactly. So I'm going to make two transitions. Make it here. The nice thing about the original transition was that it didn't read anything. So neither of these transitions are going to read either. And for the first one, as was suggested, let's push on an arbitrary symbol. I could choose A or B here. It doesn't matter. So let's just say I choose A as the thing I push. What does this transition now do then? Pop an A. It better pop the exact same thing. So I think now we're ready because the final state's all good. There's no reading on it. All the transitions do exactly one of the two operations. We're all good. Okay. Nice. So now let's start making the grammar. So what are the variables going to be? What are the variables going to be? Something that might be easier. How many variables am I going to make? How many choices for P are there?
1.
How many states are there? 5. How many choices for P are there? 5. Independently, how many choices are there for Q? 5. So how many in total? Please don't say 10, please. 25. So I'm not going to write them all down, but there will be 25 variables. So one variable will be, say, how do I get from Q0 to Q0? Another one might be Q0 to Q1. Another one might be Q4 to Q1. I'm just going to list them all out. Then the last one may be Q4, Q4. But I'll have 25 variables nonetheless. I do have to do this in general, but Are some of these variables, are any of them going to be completely useless? Yeah, like what's an example? Yeah, the Q4, Q2 or Q4, Q1, right? There's no way to go back, right? And in general, if you have your PDA representing a strongly connected directed graph, then every variable will be used, obviously. But since this is not strongly connected, not every variable will be used. We'll generate anything. So, some of these variables will be useless, but I want this to work for every PDA. I don't want to make any clever decisions here. Okay? All right. What's the start variable going to be then? Right, yeah. So from the start state to the single final state, well, that's Q0, Q3. Okay? And the terminals are easy. It's just A or B, assuming that the input output is A. So let's start making the rolls. We're making some of them, as we'll soon see. So which set of rules is the really easy one? Yeah, the ones that produce epsilon, right? How many am I going to make? 5. Because the subscript is the same in both cases. So I'm going to have A Q0, Q0 makes empty. I'm not going to write them all, but Q1, Q1 makes empty. A Q4, Q4 makes empty. But I have 5 rules there. Okay, that was pretty easy. For the second one, how many rules am I going to make? How many choices for P? 5. How many choices for Q? It's the same number every time. 5. How many choices for R? 5. How many is that in total? Don't say 15. It has 1 5 in it, but 5 times 5 times 5. I hope we know our multiplication table. 125. Do you think I want to write all of them down? So for this small PDA, which started out with 3 states, now it's 5, it has 125 rules. So do you think that a person is good for this, or do you think a computer can do this instead? I hope a computer can do that. So let's see. So I'm obviously not going to write them all down. But let's say I'm interested in my start variable, and I want to apply the second set of rules to it. Well, let's see. For this second set, I'm going to have 2 variables on the right side. 2 variables. Do I know about the subscripts of those 2 variables from the one on the left side?
It's going to start with Q0.
Right. Yeah, the first one's going to have Q0 as the starting one, and the last one is going to have Q3 ending. What about the one in the middle? How many choices do I have for that guy? I have 5 choices. So, could I choose any one to fit in the middle part here for Q? Yeah. So I gotta have every one of those possibilities, even the ones that make no sense. Like for this one, Q4 is gonna make no sense for this variable because there's no way to get from no, this one makes sense. If I, for instance, had Q3, Q4, that would make no sense. But this one does have a pass, so this will generate something. Okay? Well, let's do another one. Maybe one that makes no sense, actually. So let's do Q2, Q0. Again, it's going to make 2 variables. The first coordinate of the first variable is, again, going to be Q2. Second one of the second guy is going to be Q0. And then we got to have all 5 choices for the middle guy. Let's say Q1, because that's perfectly valid. those variables will make literally nothing, but I gotta have that possibility just in case. Okay? And I'm gonna make all 123 other rules like that. Okay? And note, I did not look at all at the PDA itself. All I did was just spit out a bunch of rules based on the number of states and the states names themselves. Okay? Any questions so far? Okay. So now let's actually make the interesting ones. So we got to make rules that involve pushing something and a matching pop, which means that the push character is the same thing as the pop character. And as we said, we don't assume anything about what the states are here. They can be completely arbitrary. So what I need to do is what? I gotta find a transition that pushes something and some other transition that pops it. The same thing. Okay, well, let's look at this transition as the pushing guy. So it pushes an A. Is there any other transition that pops an A? Yeah, there are actually 3 of them. So this is one of them, this is one of them, and here's another. So let's do this guy first. This one word vis-a-vis. So what I'm going to do, and I suggest you do as well, is I'm going to make kind of like a table, which makes my life easier. So all I'm going to do here is just redraw the transitions to make everyone's life easy. So those are just redrawn transitions. Okay, well, let's see. I know what the X is. That's an A. Does the X part show up in the rule at all? Does X show up in the rule? No, because all the grammar's concerned with is generating characters. Well, that corresponds to what happened on reading on the transitions. So, let's see. I need to figure out what these 4 states are. Well, the push part corresponds to states P and R. So let's look at the push transition here. So P is where I started before I did the push transition. What state was that? Right before I applied the push. Q0. So P is going to be Q0 in this case. Where did I end up after the transition for pushing? Q0. And that's what R is. So Q0 is there. For the pop part, S is where I started from, Q is where I ended up. So S is where I started, Q is where I ended up. Where did I start on the pop transition? Where did I start? Q2. So I started in Q2, and I think we can all figure out, I hope, that we end up in Q2 after the transition. So we actually have everything we need to make the rule. So APQ, I want to know what that is. So APQ, that's AQ0, Q2. So AQ0, Q2. Well, what's the subproblem? Subproblem is ARS. Well, RS is Q0, Q2 again. So that's my subproblem. Did I read anything on the push transition? Yeah, I read an A, right? It's right there in the transition. So I read an A. Did I read anything on the pop transition? Yeah, I read a B. So I put a B. And now we just made a roll. Okay. So in terms of the PDA, what does that mean? That says, if I want to know how to get from Q0 to Q2, one way is with the same stack type, remember. I push an A, go over to Q2, then pop a B. If I did that, I pushed an A on, And then over here, I had to pop the A off so that I get at the same stack height. Okay? So all I'm doing is modeling subproblems in terms of the transitions. Okay? Let's do one more. So let's look at another pop. So I'm going to do the same push transition, but a different pop one. So here's one that sounds interesting. It goes between two different states. So let's see. I'm going to have Q4, go to Q3, no read, pop A, push nothing. Well, the push guy is going to be the same, so I'm not going to go through that again. So for S and Q for this guy, where did I start on the pop transition? Q4, yeah. So I started in Q4, and I think we can figure out that we ended up in Q4. Okay? So what is my entire goal? I want to figure out what APQ is. Well, what is PQ? It's Q0, Q3. That's my goal. AQ0, Q3. What's the subproblem? It is RS, which is Q0, Q4. So Q0, Q4. Again, did I read on the push transition? Yeah, I read an A on the push transition. Did I read anything on the pop transition? No. So I'm not going to put mark on my shirt. I didn't read anything on the pop transition, and so therefore that rule is done. Okay. Well, what does that mean in terms of the PDA? If I want to go from 0 to 3, one way to do it is to read an A, which means an A is going to be on the stack now, and then figure out how to get from 0 to 4 via the subproblem. Then from 4 to 3, popping that one A off that I pushed on at the beginning. Okay? So all it is doing is just matching everything up. Every push is matched with the pop later. Okay? Any questions on how we were able to do this? And obviously this is not every single one, but I continue on from there. I believe there ends up being 12 rules of the last type. So I invite you to go through the details, but that's essentially how you would do it. Yeah.
I think I only choose one from these rules because you only push one.
What do you mean I only push
Yeah.
one?
Because you're matching the top with a push. You only push one in here, and you're assuming two rules, which each of them can pop the A.
Right. So I'm making two rules here. So in order to make a string entirely full of terminals, if I want to apply a rule like this, there must have been a push and a pop later. So if I generate a string full of terminals, every push matches exactly one pop. And so therefore, since I started empty, I have to end empty. So you're right. We may have a string that is not in the PDA's language and could end up either pushing too much or popping too much, but the grammar won't generate it. Because for a string that actually is generated, every single push matches exactly one pop. And so therefore, there's nothing that's left unmatched, I guess. Okay, does that make sense?
Yeah, because I just figure out if we want to pass something, we just choose the first rule, which is like we don't consider the other rule if we pass it.
If we parse it, what do you mean? Okay. Any other questions?
So it doesn't have to be from start variable, start state to final. We can choose any.
Yeah, I need to choose. I need to do this for every possible choice of one push and a matching pop. I need to do every single one. Okay. Any other questions? Okay, let's do the second question. So there's absolutely no way I could do this entire question or even convert it to a CFG in time, but I invite you to work on it at most. So let's see. Let's consider the language A's followed by B's followed by C's, such that either the number of A's and B's is the same, or the number of B's and C's is the same. Okay? What if I change that word or to an and? What would happen? How many of you were at lecture yesterday? You would know. So what happens if I change that or to an and?
It would make it not context.
To make it not context free. So I really do have to work with the or here. So in terms of the word or, how do you think that's going to help me? What does or sound like?
You could break it up into two different languages and union them.
Right, so it's just union of PDAs. How do I do union of PDAs?
So we need it.
Yeah, it's almost exactly the same. So we have two epsilon transitions, but we gotta ensure that the stack, when we get to the end of this union part, that the stack is empty in both cases. So I'm gonna make sure the stack is empty. Okay? I definitely don't think I can finish the whole PDA, but I'll give you an idea of how to do it. So let's say that this top part represents, I'm checking I equals J. So I'm checking if the number of A's and B's is the same. Do I care how many C's appear afterward in that case? No, I don't care. As long as I have the same number of A's and B's, I couldn't care less how many C's there are after. So, how do you think, what's a good strategy to approach that case? What is A to the n, B to the n? How did we do that problem? Sir?
Push A.
Yeah. So we pushed A's onto the stack, and then what did we do with B's? Yeah, pop them off in tandem with the A's. And then what was the fail-safe that we did?
Write a $sign.
Yeah, put on a special symbol at the beginning. So maybe I'll just do one then. So what we need to do is we need to push on that special symbol, $sign. Yeah, I won't do the second one because it's almost the same. So push on a $sign. Then what do we need to do? Put the A's onto the stack. So read an A, put an A on the stack. Then what we did is non-deterministically choose to start doing the B part. And then what we just discussed is that we read a B, pop an A off, and push nothing at the same time. And then supposing that we matched everything up, A's and B's correctly, then the only thing on the stack now is $sign. So I'm going to pop that guy off. And then obviously at that point I should accept because I don't care how many C's are after. But what do I need to do to that final state? What if I read a C when I'm in here? And I better stay there. So I better add a transition where I just keep reading C's and do nothing to the stack because I don't need to do anything to the stack. Okay? So that's essentially how you would do the I equals J case. For the J equals K case, what would I do differently?